the actual browser window, but welcome to another edition of Quantum Software Talks, where we find and talk to some really cool folks building quantum open source software. My name is Dr. Sarah Kaiser, and I am a technical staff and quantum community lead at Unitary Fund. Unitary Fund is a nonprofit open source kind of foundation that is working to support quantum open source software by giving out microgrants to support projects and building tools that the community needs. So if you're interested in learning more about that, check out unitary.fund. So today we have some super fun guests. I am really excited to talk to them. I actually know Kenny from a ways back in that one should never play bluffing board games with them. But yeah, we have a couple folks from the pyGSTi project. So that's pyGSTi. And yeah, which is a Python package for characterizing quantum systems, in particular with gate set tomography. So Kenny and Erik, are you good? Yep, I can. Alrighty, let's bring everybody on here. Hey, Kenny and Erik. now that people can see you.
Yeah. Well, thank you for having us.
Yeah, that's so much. We're very excited.
I'll get right into it. This is a talk on the pyGSTi, which is a software
do you
for
want
quantum
to
characterization.
Yourself, Kenny and
Oh,
we'll do that first, and then you can start talking.
Oh, sure. Yeah, my name's Erik Nielsen. I am one of the members of the QPL here, and I'm the lead developer on this pyGSTi software.
To be clear, here is Sandia National Labs, right?
Yes, here is at Sandia National Labs.
Yes, I'm Kenny Rudinger. I am a staff scientist at Sandia National Laboratories as well, although I'm based out of the Washington, D.C. area these days, and so also work on pyGSTi and sort of deploying the QCVV tools that we develop on various platforms and working with experimentalists, sort of doing a lot of impedance matching. And so we're just very excited to tell you about pyGSTi.
Like today. Literal impedance matching or like figurative between toolkits?
Well, mostly here, and in particular, sort of like between people and sort of the impedance mismatch that you sometimes have between experimentalists and theorists, because a theorist like myself will listen to experimentalists and say, aha, I know exactly what you're talking about, and of course I have no idea what they're talking about. And so dealing with very patient experimentalists as, we sort of muddle through and begin to sort of learn how to understand one another and are able to then sort of, make more scientific progress as we can use these theoretical tools to actually sort of improve the hardware. At least, that's the hope.
Yeah, it's still measured in ohms.
It's true. It is. It is still measured in ohms.
Oh my gosh, that is so good.
Oftentimes, mega.
All right,
yes.
I will get us to the slides here. Can folks on stream see the slides? First question. I think we should be good. But yeah, I will let you take it away, Erik.
Great. All right. Well, so thank you again for having us here. I'm going to talk about this pyGSTi software, which is for quantum characterization. And as we've just talked a little bit about, this is developed within this Quantum Performance Lab, which is a research group within Sandia National Labs. My name's Erik, and Kenny Rudinger will also be talking. We'll kind of be trading off here, as you'll see. So in this talk, I should kind of broadly say there are three parts and kind of three questions that I want to answer in this talk. The what, the why, and the how of pyGSTi. So particularly, what is pyGSTi? Why does it exist? Why would I use it? And then how is it used? And we'll have some demonstrations of how it's used in the talk. So let me start with the why. In a single sentence, why pyGSTi exists is because quantum computers don't just work. Today we have quantum computers that are small and noisy. To solve really great and amazing problems, we need computers that are big and not noisy. Here's a On the left here, there's a cartoon of what a quantum computer might look like, and you can see it looks a little bit more like a science lab than it does like your iPhone. And on the right-hand side is an analogy that I want to make in this talk. If today's quantum processors were like a car, then this might be the car that they are. It's, you know, it's a working automobile, but it doesn't quite do all the things you'd want a car to ever do, right? And so to make the car better, to make the quantum computers better, one of the things that we're going to need to be able to do is to understand where we are now and characterize what the performance of our current processors are, and also be able to look forward and be able to understand what's holding them back, what specific things are there that could make them better. So this is now the setting where, you know, enter pyGSTi into this. What does pyGSTi do? How does it help us address these sorts of this sort of landscape? And what is pyGSTi? Well, it is a tool. That's the what. It runs different diagnostics, and so I should actually say it's a bunch of diagnostic tools. It's a toolkit. It has many of them, as we'll see. And these different tools and these different diagnostics we call protocols, and they take in data from, you know, a quantum processor, analyze it, and give you some insight into what's not right about that quantum computer. What are the types of errors you're seeing? We can broadly break those types of diagnostics into two groups. The first is benchmarking, where you're looking for an overall performance of a quantum processor. And the automotive analog of this would be, this is like a road test, okay? So you take the vehicle out and you drive it around and see how well it like turns and how well it accelerates and, you know, if it has brakes or not. And that's great. And there's the other type of diagnostic we want to talk about is model-based characterization. So model-based characterization seeks to build a detailed error model for the quantum processor so that we can understand some of the nitty-gritty, what exactly is not working, what are the types of problems that we're seeing with it. And this has a particular eye to making a next generation of hardware where we can eliminate those types of noise and make the hardware better. And the analogy here would be of this device you see on the lower right. That's a scan tool for people who aren't familiar. This is something that if your car was built after the year of 1995, your car has a little port that you can plug this tool into, and it'll tell you something about what's going wrong with the car. Like there's, I don't know, a misfire in cylinder 4, and it doesn't tell you exactly what's going wrong and what you need to do, but it gives you detailed information about where in the car something is wrong. Broadly, this whole kind of diagnostic arena we refer to as quantum characterization, validation, and verification, or QCVV. So this is this is what pyGSTi is at its core. As I said, there's a lot of different diagnostics within pyGSTi. I mentioned some on the previous slide you may have noted. Here's a more full list of them. These are complementary. These are a lot of tools that they work on different numbers of qubits. They give different types of outputs. They're useful in different ways. I'm not going to go through all of these. We'll touch on some of them, mainly the gate set tomography and randomized benchmarking a little bit more. But realize, I think a key piece here is to realize that though pyGSTi has GST in the name, that's for gate set tomography, which is just one of these protocols, it has now grown into a suite of protocols that is much more than just gate set tomography. So so this is, again, the what of pyGSTi. I want to take a step back and answer another why question, which is, okay, so we have this problem, we know what it is, why would you use pyGSTi though? Another way of phrasing that would be, what is so difficult about these problems that we should have this software package? Why can't I just write my own? And so in the next two slides, I'm going to highlight in particular some of the difficult parts of the two types of diagnostics we've been talking about, the benchmarking and model-based characterization. So this slide is for the benchmarking. And remember, this is an overall performance metric we're trying to get out of a quantum processor. Here, most protocols do something where they run lots of random circuits or programs on the quantum computer. And they see how often the quantum computer fails to give the expected result. And as you make the programs more complicated, typically the circuits get longer, it fails more often. And in the cartoon kind of drawing at the right here, you can fit a slope to how quickly that falls off as you make the programs longer, and you can extract from that an error rate and say this is an overall performance metric for the quantum processor. Now, what's difficult about this? Certainly the line fitting here, or typically it's an exponential curve that you fit, that's not actually so difficult. But choosing the circuit family to begin with, that is not always trivial. We need to find circuits where we know the outcome ahead of time. And we also need to be able to sample from whatever random distribution we're drawing from, and that's not always an easy thing to do efficiently. So for instance, sampling from the 2-qubit Cliffords. So those are both hard pieces of the benchmarking problem. Now, model-based characterization, that again seeks to create this detailed model for the performance of the quantum processor. This has a bunch of more challenging technical pieces that even more than the benchmarking that need to be addressed. And first, I want to just run through what this is. So the picture for model-based characterization is you have a model, that's the black brick at the top there, and it has a bunch of parameters. Think of things that you can kind of tweak or knobs you can turn. Along with that, you have data from a bunch of circuits that you ran on a quantum computer. If you compare the predictions of the model and the data that you've taken, you can compare that using a likelihood. And if you maximize that likelihood, then what you've done is you found the best fit model given the data. That's essentially what gate-set tomography does. We find a best fit model, and that gives us some insight into the errors that are in this quantum computer that afflict it. Now, there are a number of technically challenging pieces about this. First, just implementing these efficient models, somehow being able to run and evaluate models on many qubits, that's a difficult thing. And we have a dog. Okay, so also, though, even before we get to the model, there's the data. How did we get the data? We needed to know what circuits to actually run that would give us data that was sensitive to all those different sliders on the model. That's a difficult problem. Simulating the circuits is known, that's just an exponential in the number of qubits hard problem. And there are lots of, a lot of good research that's done on solving that problem in its own right. And then optimizing the space. Once you've done all of this, optimizing over a high dimensional parameter space, a problem that's non-convex, that's hard. So these are all reasons why pyGSTi, right? Why it exists, why it's useful, and why you don't just want to implement it all yourself.
So the real question is,
now,
how many parameters does your dog take to describe him?
Yeah. Whether it's inside or outside the house is one parameter.
It depends on how noisy he is.
Yeah. Yeah, I suppose it could be a lot. Yeah. No.
Sorry. Dogs are always good stream companions.
They are. So let's see, where was I? So I want to go back and look at pyGSTi now as a software. This is another way of answering the what is pyGSTi, but more from a software engineer's perspective, not as a researcher's perspective. So from that perspective, pyGSTi, well, it's a medium-sized Python project. I mean, it's written in Python. It's around 150,000 lines of code. It's open source. Its license is the Apache 2.0 license, which means you can do just about whatever you want with it. One of the things that our research group has tried to do is to make this a software product, though, that other groups can use, and a way of sort of putting out, in addition to the papers we publish, the techniques that we use. This is a way of disseminating them and letting other people play around with them, improve them, etc. And so we've tried to add good documentation for the package, and also have tried to keep a lot of testing done on the package so that it doesn't just kind of break randomly with the updates that we add. So that's sort of what pyGSTi is in a nutshell from that software perspective. Now we've talked about both the why and the what of pyGSTi. And so now I want to transition the talk into the how. How do I use pyGSTi? Well, there are three main ways that we've seen folks use pyGSTi. The first is a standalone tool. The second is within within a broader kind of Python tool chain. And the third is using it in a very customized way to almost make a custom QCVV protocol, if you will. And I'll refer to each of these as different use modes. So we're going to look at three different use modes and give examples of each of these in the following slides. First, I want to expand upon each of these a little bit and draw your attention to the diagrams on the right of this slide. The first, the standard QCVV tool mode, that's where the user interacts with pyGSTi mainly through text files. You say, pyGSTi, I want some circuits to run to do gate set tomography, and it spits out a text file, and you run those circuits on your hardware, and then you put the results in a data text file and send that back in, and pyGSTi crunches a bunch of stuff, and out comes an HTML report, we call it. So it's just like a web page showing you the different results, and we'll give a demo of that. The second use mode, the user uses pyGSTi as a subroutine within Python code that they've written. And oftentimes experimental groups we've found will use Python as a way of controlling the experiment in different fashions. And so this is an easy way to integrate some of that characterization into their tool chain. The third way, this customized protocol approach, instead of the user code calling pyGSTi as a subroutine, the user can write code that pyGSTi calls as a subroutine. And this effectively customizes what pyGSTi would do to run a protocol to the particular problem the user is trying to solve. And we'll give an example of that too. Before we get to the examples, and I give it over to Kenny here, I want to show you just in broad strokes, what's the flow for running a protocol in pyGSTi. This is how you run a protocol in pyGSTi. You first create a protocol object. You then create for that object an experiment design, which is a list of circuits. It's called an experiment design because it is essentially designing the circuits you want to run on the processor, and that's, an experiment design. So you take this experiment design and you run it on the processor. That is, you execute circuits on the actual quantum hardware, and that produces a data set. So you've got that little picture of a chip and the arrow to the data set. You actually may be able to see and the data set packaged with the experiment design is an object we call a protocol data object. Oh, did someone say something?
I don't think so. I don't know if
Okay.
something should have changed.
I was just getting a little audio.
I know, I heard it too. But
okay.
Let's just
not going
hope
crazy.
it disappears. It's the ghosts.
Yep. Yeah. So with this protocol data object, this has packaged all the things that you need all the inputs that you need to run a protocol. And so the protocol object itself has a run method, and you hand it a protocol data object, and it returns a protocol results object. Then you look at the results, and that's the flow. So Kenny's about to describe now, give examples of this, and you'll see this flow through what he's about to show you. We'll go through the different use modes in the examples, and so we'll start with use mode 1. And so,
great. So yeah, so we're going to start with an example of using pyGSTi as a standalone QCVV tool. So situations where you don't have very low-level interaction with pyGSTi. It's relatively high level, as Erik explained a few slides ago. And this is in general particularly good if you want to have, to generate a GST HTML report so that you maybe have a pretty full description of your system, which you can either use, you can sort of dig into sort of understand better what's going on, or you just have some high-level graphics that you give to your PI or PM and hopefully make them happy. But you're not necessarily going to be going in and digging into the guts of pyGSTi to try to understand all of the various objects that it generates. And so I will say that all the code we're looking at here has already been run. Unfortunately, because of the technical difficulties, this is not a live notebook, so won't be able to actually to run anything here directly. Although please feel free to ask questions about anything that you'd like to see, and we can try to run it in real time if possible. These notebooks will be available afterwards. And we also have a whole suite of tutorial notebooks available through the pyGSTi GitHub repository. So with that in mind, what we're going to do for this particular demo, we're going to run GST on just a very simple gate set, a single qubit gate set with x pi over 2, y pi over 2, and idle gates. And this is a sufficiently common use case for us with this particular gate set that we actually have a pyGSTi object called a model pack that actually contains sort of all of the pieces necessary to build a GST experiment for us without us needing to specify lots of low-level information. So we're going to make an experiment design here on line 3 just by calling the create GST experiment design function, and all we have to pass in is the maximum circuit depth that we want for this particular experiment design. In this case, we choose 32. So we have an experiment design object, and this is going to tell us what all of the circuits are that we need to run, along with some additional auxiliary information. We can write this to disk, and so now we have a protocol data folder that's got a bunch of files in it telling us sort of how to do the analysis on the GST analysis at some point in the future, as well as a file that has all of the circuits. It's sort of an empty template dataset file that the experimentalist will then fill in with the actual data that they got. Or you fill in with some data that you simulate yourself. And so for this particular instance, we're just going to go and simulate some data. I'm not going to talk really about how that gets done right now, but we'll come back a little bit later and talk about how one can do simulations. So once you've gone and made the data, protocol data, you can go and load it in from the directory, and then you just run GST. And to run GST, you make a GST protocol object, and then you just call the run method of that protocol object on the data object. And GST runs, and in this particular instance, it takes about 30 seconds to go. And once you're done, you've got a results object. And with the results object, you can go and make an HTML report. So you just make a report object, and once you've got the report object, you call the right HTML method, and now you have a nice HTML report. This also takes about 30 seconds. So Erik, if we can flip over to the HTML report.
I seem to have hid my tabs.
Ooh.
Related question though. So with the protocols, are there a lot of choices for the protocols? How do I know which protocol is the right one to choose? Like, or is that just something that I talk to my collaborators about and we try to work out, from theory?
Well, so I think it depends on what you mean precisely. So I suppose there are multiple different questions one might want to answer in some sense. We say, what protocol do we use? So if you say, well, I want to do GST, then you're going to use a GST protocol. Right? If you say, oh, I want to characterize my system in some particular way, but I don't know which particular way I want to, right? That's sort of a separate question. So are you asking about, like, if I know I want to do GST, how do I pick the right GST protocol? Or do you mean to say sort of, how do I figure out what protocols I want to run to do sort of arbitrary characterization of the system?
Definitely the latter. Like, what if I'm not sure which is the right approach because I'm a new grad student and someone just gave me controls to the dill fridge and set me loose?
Yep. Yeah, I mean, I think that's a really excellent question. I think that it maybe depends a bit on what it is precisely that you want to learn. If you want to know, what are the process matrices for the gate operations that you think you're implementing in your fridge, then you would probably want something like GST. If you are sort of concerned about sort of higher level holistic understanding of the device, then you might want one of the several different flavors of randomized benchmarking. But I think this is a really good and sort of deep question. And I think that, it's very much going to be sort of context dependent. And certainly one thing that, you always can do is you give us a call and tell us about your system, and we'd be happy to talk with you and try to figure out, what QCVV solution is right for you.
That's go door to door, lab door to lab door. Which QCVV solution is
precisely?
No, that makes sense, and I get there isn't like a go-to answer for everything, but it's something that I've questions that I've had, and some
Sure.
of my previous collaborators, actually, like Broken Mirror, who's on the chat here, always says, like, start by writing down what question you want to answer. And that's
Right.
always a good place to start.
Absolutely, and to be fair, I really appreciate you pointing this out. So, sort of implicit in what we're talking about here is, we've already skipped that step. We sort of have implicitly assumed that we know that we want to do GST, or we know that we want to do RB. So assuming that you wanted to do GST, then this is what you would do. So Eric, you want to flip over to the HTML report? Great, thank you. So this is a GST HTML report, and we could spend the rest of the time from this tutorial talking about all the details in here, because it really has got just a whole bunch of information, and we're not going to do that. But I'm just going to highlight a few high points about this. So the first thing you might want to know about your gates, about your system, is how good are they? Right? How close are they to the target operations that you want to implement? So here on the summary tab, in table 1, we've got a table that tells us various error metrics, entanglement, infidelity, diamond distance, some other things about how good the individual gates are. The other sort of really important thing, though, that we have on this slide, or on this tab, are the model violation summaries. So a really important thing that we want to know in general about any sort of quantum information processor is, and if we've done GST on it, we have some estimate for a model for it. Does our model actually fit the data? Do we have are the assumptions that went into our model? Do we have Markovian noise, for example? Do we actually successfully model the data, fit the data with models of that form? And so that's sort of what figure 1, the model violation summary plot, is telling us. So if you have a small n sigma, this means that indeed you're fitting the data very well. And if it's quite large, then you're not. Maybe you've chosen a bad model, or maybe you've got a lot of non-Markovian noise. And as Eric is pointing out, by clicking on the various titles for the tables and the figures, you can get expanded captions, which will tell you a lot more detail about what all the individual pieces of the report are telling you. The other thing I'll point out very quickly, Eric, if we flip over to the raw estimates tab, we can see the actual estimates of the gates, the gate process matrices themselves. And so we have this column of target superoperators. This is sort of a heat map plot of what we expect a perfect gate to look like, and then if we, in the right column, we have what we actually have reconstructed. And by eye, you can't actually tell the difference between them, but if you mouse over the individual cells, you'll see that you get the actual numerical values, and you see that indeed they are not, the white ones are not precisely 0. And the blue and red ones are not precisely -1 or +1. If you want to actually have access to these arrays and to do things with them, you can extract those from the results object in pyGSTi, and we'll come back to that point a little bit later. So there's a lot more in here that is sort of interesting and neat, but I think because of time constraints, I think we'll just go back to the code. Okay, so now what we're going to do is we're going to do RB. And to do RB, we're not going to actually go and generate an HTML report. We're just going to use a Plotly workspace. So we're going so we get the results actually plotted inside the Jupyter Notebook. So we make a workspace instance, and then we make what is called a processor spec. So a processor spec, you can think of it in some sense as a description of the quantum information processor that you want to characterize. So you tell it how many qubits it has, what the names of the qubits are, and what the names of the gates are. And if you pick from a list of a select list of gates that pyGSTi already knows about, you don't even need to tell pyGSTi what those gates mean. It already knows. So it knows that GX-pi2 is an x-pi/2 rotation, and GX-m-pi2 is a -pi/2 rotation about the x-axis, and so on. So with the processor spec in hand, we can now go and actually create an experiment design for randomized benchmarking. So there's some additional information we need to specify, what the circuit depths are, how many circuits per depth we want, how we're going to compile everything. Once we've got all those pieces, we make an experiment design. So again, just like we had a GST experiment design, we now have a randomized benchmarking experiment design. We can use that to make an empty protocol data folder. And we're going to now make some data and populate the folder with that data set. We'll load it in. And just as we did with GST, we're going to make a protocol object. We're going to make now an RB protocol object, and we're going to call the run method of the protocol object on the data. And once we've gotten that, and this is going to run very quickly, it's about 5 seconds or so, we can make a plot. Now, unfortunately, it's not plotting. Do we, I suppose, Eric, if we actually just went and, this is a problem with.
Just try again to see if it'll load. I'm not sure if it will.
Do you have to run this yourself directly?
I think it should be in the Jupyter notebooks are a little funny. Did I already pass it? Let's see.
Yeah, it's up a ways.
Oh, sorry.
Yeah,
so it looks
like should be
it
there.
Might, because we transferred it from your laptop to mine, maybe. But usually this would show just a decay curve, like an RB decay curve that you could also mouse over, and it would show you information about it.
And it would also tell you what the decay rate was. So you could get individual data points for each of the circuits, as well as sort of a little box and whisker plot. So you could see the distribution, and then a best fit curve showing the decay. So please use your imagination and accept the knowledge.
It's the teaser for running these yourself afterwards and checking it out.
Right. I'll talk to a couple more slides. So that was all use case, the use mode 1, where we looked at the entire, we kind of used pyGSTi and interacted with it using these text files and got a report object or a nice kind of pretty decay curve if you use your imagination there in the randomized benchmarking case. Now we're going to look at the use mode 2, where it's more incorporated into a tool chain, into another like Python script that you have to run experiments. And so to do that, I think it will be helpful to take a little bit of a deeper look into what's inside the protocol objects in pyGSTi. And inside those, they use 3 main ingredients, 3 main like Python objects that pyGSTi uses over and over again in these. And so you can think of it as mixing these ingredients in different ways and just making lots of recipes, lots of protocols, that is, out of them. For example, and I should say, so these 3 main ingredients are circuit objects, model objects, and dataset objects. And those are kind of self-explanatory. A circuit is a single quantum circuit. A model is something that models quantum circuits and can predict the outcomes of quantum circuits. And datasets hold data that you've taken on an actual device. So for instance, circuit simulation, it takes a circuit and you have a circuit and a model, and the model can simulate the circuit to give me outcome probabilities. If I'm testing a model, then I take a bunch of circuits and a model and see if those predictions match a data set. GST takes a bunch of circuits and a data set and then produces a best fit model for them. Randomized benchmarking does something similar, where it takes a bunch of circuits and a data set, and it produces a randomized benchmarking number by fitting to the curve given by the data. So again, kind of expanding these protocol objects and looking in the inside, gate set tomography or model testing, it takes in a bunch of circuits. That would be the same thing as the experiment design objects, as we've seen before. And the protocol takes those circuits, and a model simulates the circuits to give me outcome probabilities, whereas the data set is the result of me actually running those circuits on a actual device, and I get outcome counts. If I compare the predictions to the actual outcomes I've observed, I can compare them using a likelihood function. And if I maximize that likelihood function by tweaking these parameters up here, I obtain the best fit model. And so that's what's going on inside of this protocol. In a very similar way, randomized benchmarking has the same components, except the model is more or less replaced by a curve fitter that we fit the success probabilities that it predicts to the frequencies that we observe, the success frequencies from the data, and we just minimize the sum of squared error. That's essentially what the exponential fitter is doing, and we get a RB number out of that. So we'll pay attention to this as we go through an example or two showing the next 2 use modes. So that's, incorporating it into a workflow and also customizing a protocol within pyGSTi. So I'll hand it back over to Kenny for that.
Thanks, Erik. So, great. So what we're going to look at now is we're going to look at another example of running GST. But what we're going to do here is we're going to change things a little bit. We're going to run this on a custom model, so not one of these default model packs that pyGSTi comes pre-bundled with. And we're going to actually then look at sort of the constituent pieces of the GST results object to see sort of, how you can interact and interface with what pyGSTi is spitting out in a procedural way, so you could actually make it part of a workflow if you wanted for calibration, for example, or something to that effect. So what we're going to do is we're going to do GST on, let's say, an H and T gate set. Okay, so Hadamard and T gates. So we're going to start by defining the H and T gate set, and we're going to make a processor spec, and we're going to say the gates that we're going to give it are called GH and GT. And pyGSTi conveniently already knows about GH. It knows that that's a Hadamard, but it doesn't know about GT. So we have to do some T-gate injection, if you will. And to do that, we're going to define a unitary gate UT, that's just line 3, and we're just defining it as a numpy array using scipy.linalg.explim to do a matrix exponentiation to make a numpy array object, just a 2x2 unitary. And then we tell the processor spec, hey, this gate labeled GT, well, it's this unitary object, this numpy array UT. And then we can, from that, create a target model. So the last line, our target model HT contains the Hadamard and T gates. And then we say, oh, wait a second, actually, I want to add another gate. I want to put in a T dagger. So I could go and I could modify in 19 just by specifying a UT dagger as well. But because model objects are dictionary-like objects, we can also directly access them and stick in additional gates. So that's what we're going to do in this next cell. So you see sort of a lot of flexibility in how we can put in gates. And because we're still putting in process matrices, I define the unitary gate, that's line 1, but then I have to convert it into a process matrix in the Pauli basis. So that's what we're doing on line 2 with this pyGSTi.unitary to Pauli gate function. And then we can go and take a look at the model itself, so we can print it, and it pretty prints nicely for us, and so we get these arrays that correspond to the process matrices. We can go, and then if we want to look at an individual gate, we can do that as well. And if you want to actually go and say, multiply gates together, well, you can do that also. So that's what we do in N23. We take GT and GT dagger, and we can just dot them together, and conveniently, as we would hope that they would be, they are to machine precision. The product of those things gives us the identity. So we've made our model. What we're going to have to do next, though, if we actually want to do GST, is we need to have all the various constituent pieces necessary for the experiment. So in addition to needing to know what the target model is, we need to know a collection of subcircuits that we classify as what we call preparation and measurement fiducials and germs. And the details aren't super important, but these are just sort of ingredients that we need for GST. And we don't necessarily know off the top of our heads what these subcircuits that get put together in certain ways look like. We know how to put the circuits together, but we don't know what these subcircuits are. And so for the pre-existing model packs, we already computed those. We know what they are. If we don't know them, though, conveniently pyGSTi has fiducial selection and germ selection routines that will tell us what the fiducials and germs should be. And so once we have generated them, we can then just write them to file, so we can email them around and load them in another session. Or if our laptop crashes right after we've gone and generated them, not all is lost. For single qubit case, by the way, this generates very quickly. It takes sort of non-trivially longer period of time to do this for 2 qubit gates, for 2 qubit models. But once we've got the germs and fiducials and model built, we can actually go and create an experiment design just as we did previously. We specify what our maximum circuit depths are. We make our experiment. I was just
going to ask, can you give
yes.
what is a germ and a fiducial? Like just TLDR, like is it a matrix? Is it what are they?
I'm sorry. Yes. So I'm sorry. These things are subcircuits. So a fiducial is you can think of this as a subcircuit that you use to prepare a state in a particular basis or to perform a measurement in a certain basis. So I want to prepare some informationally complete set of input states that I'm going to use to tomograph my processes, and I want some tomographically complete set of measurements in order to properly tomograph the processes. And so the fiducials make those bases. You can imagine you're using them to sort of simulate preparations and measurements in different bases. And a germ is a short circuit, a short subcircuit that then gets repeated some number of times so that we amplify our sensitivity to the underlying parameters that are inside that germ. So for example, if I take my X gate and I want to learn just about the spectrum of X, well, I can get a decent estimate of that by tomographing the gate X. And then if I tomograph in addition to that X times X, I can get higher sensitivity. And I do X to the fourth, I get even higher sensitivity, and on and on and on. We logarithmically space these things so that we get Heisenberg scaling in our accuracy instead of standard quantum limit scaling.
Perfect. That makes a lot of sense.
But then, excellent. Good. And the only other thing I'll say then, because we care about things other than just the spectra of these gates, we care about their eigenvectors as well. We're going to wind up combining gates too. So if I care about say the angle between an X rotation and a Y rotation, the angle between those rotation axes, I might want to look at a germ that's something like X times Y. Okay. So does that make sense?
Yeah, I think so. I just wanted to because I don't think those terms are terribly common elsewhere, maybe, but obviously are related to things that are and Eric, what you wrote down there was very helpful. So thank you.
Yes, thank you, Eric. Eric said in 2 lines what it took me,
Sorry
much
for
longer
I just wanted to figure that out.
No. It's a great question. Thank you. So before we actually go and run the experiment, let's just look at the circuits for a minute. So here's a list of all of the circuits in our experiment design, and we're going to look at a couple of them just very briefly. So we're going to look at the 1st and 16th circuits, and you can look just at what the default representation of these things are. So these, if we look at out 32, the way to read this is given in gate operation order, not matrix multiplication order. So you read this as do GT on qubit 0, followed by GH on qubit 0, and then measure qubit 0. You can print it, though, and get a nice ASCII art picture instead. This, of course, is perhaps not publication grade quality graphics, but good enough that you can get a nice understanding of what the circuit looks like. And then we can also look at, say, circuit 16, which has some more gates inside it. And if I want to know what the actual probabilities of success are, the outcome probabilities are for these various circuits, you can just pass these circuits to the probabilities method of a model. And then it does the matrix multiplication for you and just gives you a dictionary for the various outcome probabilities. So now, with that in mind, we're going to make a noisy model to simulate the data. Okay. And there are a bunch of ways that you can make noisy models, but I've given just one sort of simple example here. I'm going to, for the GT and GT dagger gates, which I want to put some noise on, I'm going to define them just as I did earlier, except that you'll notice that where it's we've got pi over 4 at the very end, I'm adding 10 to the minus 2. So I'm putting in 10 to the minus 2 over rotation error on the T gates. I'm leaving the H gate alone. I'm not putting any unitary error on it. I am, however, at the end, I'm going to call the depolarize method of the model object itself to depolarize all of the gates. In the gates, I'm going to depolarize by 10 to the minus 3. I could, if I wanted, depolarize the spam noise as well, although I've chosen not to here. So there are a whole bunch of different ways that you can inject noise into your model. And you can always just provide a process matrix as the simplest thing, but there are other methods one can call to put noise in. So now we can, again, as we did previously, write the protocol data. We can then simulate the data, just given the noisy model and our experiment design and the number of shots. We write it to file, and then we can read everything, read it all in, and then we can run GST on. Just as we have done previously, we get a GST protocol object, we call its run method, now we have a results object. We can go and make an HTML report, and so that's what we do here in 44, but we're not going to look at that right now, because we've already looked at an HTML report. We're going to now actually look at the results object itself. If I want to learn about the results object, and let's say I forget how do I access things, conveniently the results object will tell you. So just say print results, or here results HT, and it's going to tell you how to access everything that lives inside it, everything that it contains, and how to get to it. So we want to look at one of the estimates. Let's look at the CPTP estimate. This is GST. This is the pyGSTi's estimate of the completely positive trace preserving model, the best completely positive trace preserving model that pyGSTi can come up with to fit the data. Okay, so I want to say, well, show me what you've got, print CPTP estimate, and it tells you how to access things inside there as well. And what you typically are going to be interested in is what's called the standard gauge opt. This is the final estimate because GST works iteratively. You have a collection of a series of estimates. You take the final one, you gauge optimize it to the target gate set, and that's what the standard gauge opt key is going to give you. So we're going to look at this final gauge optimized model, and we can print it out. That's what we do in N47. So if we scroll down, we can see all the output for N47. So wait a second, this isn't quite what I expected. Previously, when we printed models, we got a 4x4 array for each individual gate, and that's not what we have here. What's going on? Well, because the CPTP model is indeed CPTP, it has this very nice parameterization to make things a bit more compact. Instead of storing a dense 4x4 array, it stores a 2x2 unitary array along with a vector of error parameters that pyGSTi knows how to compose with the unitary operation to make the full noisy gate. And if you want to actually look at the noisy operation as a dense matrix, you can just call the toDense method. That's what we have in the subsequent line. And then we can dot these things together or do whatever it is that you would like with them. The other thing that's really cool is because this has a CPTP parameterization, you can get out actual error rates that hopefully correspond to some actual physical processes, like Hamiltonian errors or stochastic errors, and that's what we've got in 50. What we're printing out, and in point of fact, you can actually see these error rates in the HTML report as well. Now, one thing that you probably often find yourself asking if you work with a lot of simulated data is, how close is my estimate not to the target gate set, but to the true gate set, right? You can't ask this question, or you can't answer this question, I should say, for experimental data, but for simulated data, you certainly can. So in order to answer that properly, we've got to gauge optimize our estimate model, our estimated model, to what we know the true model is, and then we can look at our favorite metrics, like say diamond distance. And so we can do that here. We do this for the T gate, and we see that we are off by about 2 × 10⁻³ So we did, a pretty decent job. So with that, I will turn it back.
Well, I think, Kenny, that was an example of the kind of use case 2 for use mode 2.
That's right.
That's right. And I think one thing to say there is that this sort of expanded how we ran gate set tomography. At any point, you could sort of put your own Python code, right? So this, there's all these different places where you could just do a part of this or stop it and end it wherever. And so I think the illustration here was showing how those single calls to like protocol.run can really be expanded into lots of different steps that can be interacted with at any level. But then I think we were going to do this example on would now be use mode 3, where it's customizing a protocol.
And so what we're going to be doing here is we're going to be making our own object that pyGSTi itself is going to be calling when it does its optimization routines. And so the scenario that we're going to consider here is, you imagine you say, I want to do GST on my gates, but I know that the noise model that I have that properly describes my gates is something much more compact than what pyGSTi is considering by default. It's not some dense map where I have to worry about 12 parameters per gate. I know that I only have, say, for example, to worry about depolarization and over-rotation. Or maybe there are other error parameters, but I know what they're precisely, so I can put those in, I can make them static and fixed, and all I want to extract, all I want to learn about are, say, over-rotation and depolarization. So we're going to make a custom gate class. It's going to inherit from the pyGSTi dense operator class. And I'm not going to go too low level into the details here. I'm just going to point out this from vector method on line 14, where this is how we pass in a list of parameters, and the gate knows how the object knows how to turn this into a dense gate, so then it can actually do the proper matrix multiplication to compute outcome probabilities. And so here we just are going to consider a depolarization amount and an over-rotation amount, and we tell this object how to convert that into an x pi over 2 gate that also has over-rotation and depolarization error. So then we can scroll ahead, and we're going to just sort of propagate this through in a pretty straightforward fashion to make a target model that has an x pi over 2 gate and a y pi over 2 gate and an idle gate. But the difference is we're going to now stick in this custom gate inside the model, and we're going to make an experiment design that's going to essentially look the same as it looked previously, except that we pass in this custom model so that pyGSTi knows that when it goes to do the optimization, that it's only trying to find a depolarization parameter and an over-rotation parameter for the X gate. We can make a custom noise model, and we're going to pass in to populate, to put in non-zero noise on the X gate. We're going to call the from vector method and pass in a vector of 0.05 depolarization and 0.1 over-rotation. We'll make some data. We will make a GST protocol just as we have in the past. And then we're going to run GST on it. Okay. And we scroll down, and once that's all done, we can again look at the results as we did previously. So we can look at the result. It'll tell us how to get to the actual estimate. We can look at the estimate. We can print out the estimate. We see, these 4x4 arrays, but that's sort of in some sense less interesting for this instance. We wanted to know what was the depolarization, what was the over-rotation. So we can extract those parameters directly from the estimated gates, and that's what we do here. And so we see that we managed to pretty closely nail down both the depolarization and the over-rotation with sort of this much more compact description of the gate, because we knew that that this was sort of a valid model to use. And I'll point out that suppose you say, I know what my model is. It's some compact reduced model, but it turns out that you're wrong, right? GST or pyGSTi will still do what it can to fit the data, but then when you look at how well you fit the data, how well the model fits the data, you'll just see a lot of model violation. You say, maybe my model wasn't, it wasn't actually that good. So that you can also use this not just for populating models and sort of understanding what the precise model parameters are that describe your system. You can also use this for model testing and saying, can I actually describe my system with some particular compact model that I've chosen to write down? So with that, I'll turn it back over to Erik.
Thanks. So that was examples of the remaining the last two use modes. And now we just want to do one more thing if we have time. We'll see how angry Sarah gets as we go here.
You're good.
One of the great things, and one of the newer things in pyGSTi is an ability to run multiple protocols, not just one. In all of the examples we've shown so far, as I think questions have been brought out, we decided, well, we want to run gate set tomography. We want to run randomized benchmarking. Which one do we choose? We could only choose one. There's a lot of framework that's been added to the package recently that allows a user to run many protocols on a single device in a very structured way. And this, we think, is a really great way to do things. It's a paradigm shift in a way, because it makes the whole analysis device-centered rather than protocol-centered. It's not, this is what happened when we ran GST on this device. It's, this is what we got from this device. And that seems like a more useful path forward to us. So in the example that follows, we'll see how we can use a number of different experiment designs and arrange them as nodes in a tree. So each one of these circles that I've drawn would have within it an experiment design a corresponding data set, and any number of protocols that would run on that data. So we could, for instance, have a experiment design that we'll call a combined experiment design that includes all of the circuits for GST on qubits 1 and 2, RB on qubit 1, and simultaneous RB on qubits 1 and 2. This experiment design, in turn, has different pieces because it's simultaneously randomized benchmarking on qubit 1 and on qubit 2. And being able to then just look at everything, this one highest level experiment design, you can run an analysis that supports many protocols on it. And that we think is really cool. So I'm going to let Kenny go back now and give one final example on this device-centric characterization as I try to change tabs again.
So which is harder, characterizing quantum devices or being able to share a screen? For me, right. It's definitely the latter.
Yeah, I think so.
So for this final example, what we're going to do, we're going to sort of put a bunch of these pieces together. We're going to do GST and mirror randomized benchmarking, a particular flavor of RB. We're going to do both of these things on IBM Q hardware. And so what we're going to start off with is we're just going to we're going to interface with QCVV as well. So we need to load our account. So you'll have to have a QCVV account, and we're going to then just define the experiments that we want to run. So here we're going to do 4-qubit mirror RB. And again, I'm not going to go too much into the details here, but we are going to define all of the negative gates that we want to run here. We know from having looked at an IBM device what the connectivity graph is, so we stick that into this availability dictionary, and we build a processor spec that is sort of a nice description of the IBM device. And again, we provide the compilation information and then the depths that we want to run RB at, and the number of circuits that we want at each depth. So we then make the MRB design. So we have an experiment design for MRB, just like we had an experiment design for regular Clifford randomized benchmarking earlier, just as we had an experiment design for GST earlier as well. We're going to define a single qubit GST experiment as well. So we do that here on N9, and that's also pretty straightforward. And now we're going to make a combined design. So this is like, as Erik was talking about, sort of this tree structure. So we use the combined experiment design function, and we pass it a dictionary that contains all of the constituent experiment designs that we want to run. So we have, in this case, an MRB design and a GST design. And now what we're going to do is we're going to actually go and build the experiment to run on IBM hardware. And so we have a submodule in pyGSTi called IBM Q. And what we're going to do is we're just going to pass in the combined design, the processor spec describing the machine, and then some additional information that you need to give it in order to be able to actually make the jobs that get ported off to IBM. So, you need to have some number of circuits per batch, because you can't send a batch that just contains hundreds and hundreds of circuits to IBM. It won't run. At present, you can run up to 75, so that's what we're doing here. Now, if we take a look at the individual circuits, we can sort of just a brief demo of how we translate the pyGSTi objects, the circuit objects, into things that IBM can digest. So here is one of our MRB circuits. So we print that out. Here's the ASCII art again. And we need to convert all of these circuits into things that IBM can run. And so in particular, we're going to just use the convert to OpenChasm method that is a method of the pyGSTi circuit object. And this all gets done under the hood. So we're not going to manually do this for all of them. This is just a demo to show how it's done for one of them. But you can now see that here we print out, we've now taken our MRB circuit and turned it into an OpenChasm circuit from a pyGSTi circuit. And I'll just also very quickly point out that in addition to the convert to OpenChasm method, we also have convert to Quill, if you want to run on Rigetti hardware, and we also have a convert to Circ for Google. And if there is sufficient interest for other conversion methods for other platforms, we might be able to make that go as well.
I vote for OpenChasm 3 and QIR.
Excellent. We should have our people talk to your people.
And I think I skipped over it earlier, but we can accept pull requests. Maybe I mentioned it. So you could implement it.
It's true. And the Circ conversion method was from some people at Google,
right.
I believe. So yeah, always happy for that. I think, yes, I don't know if Erik mentioned this or not. But yeah, we do accept pull requests. There is a contributor license agreement that you have to sign because we're a national lab, and them's the rules. But yeah, we're absolutely happy to interact with the community at large and have people make pull requests. So if we scroll down, now we're going to submit the job. So we just have, for this combined experiment object, we just call the submit method. And then it takes a little while sometimes because it was a bunch of jobs, so it's got to wait in the queue for a bit to get everything through. In this particular instance, it took about, I think, maybe an hour and a half or so to get all the way through. But once all the jobs are submitted, Erik, you can scroll down to monitor jobs. So it took about 5,900 seconds to get everything through. But then once it's all been submitted, you can monitor the jobs, and you can see that once they're all done, then you can retrieve the results, and this is very quick if the jobs have finished. And once you have the data back, now the protocol data lives inside the this combined experiment object, and so you again just make a GST protocol. You can make an MRB protocol, and you just call the run method from these protocol objects again on the protocol data that lives inside the combined experiment object. And you can go and you can make a GST report. And so now, Erik, if we flip over to the IBM Quito report, I don't know, do we have that one open? Yes, there we go. Thank you. So now we see what a GST report on actual hardware looks like, and you'll notice that we have a non-trivial amount of model violation. So we didn't really fit the data particularly well. There's certainly some sort of non-Markovian error here, but this is not entirely unexpected. It took over an hour and a half from start to finish, and so if there's any drift at all, GST can detect that. And tell you, wait a second, I can't actually fit, a single model here. You didn't really get a good snapshot of a single individual device. To get sort of more information, more diagnostic information about this non-Markovian noise, if we flip over to the per sequence detail tab and wait for a minute while things render, we now have a graphical representation of the entire GST experiment. Where what we're looking at, each individual circuit, each individual pixel corresponds to a single circuit, and these are organized, each box going across and down. These 6x6 grids correspond to different state preparation and measurement fiducials. Each of the each row corresponds to a different germ, and each column corresponds to a different depth. There's a number of repetitions of that germ. The boxes that are red correspond to circuits where we fail to properly sort of to for those we have investment model and how well predict that particular.
Hey, Kenny, is there some loud background noise? Because I've got something kind of interfering.
I'm hearing it through the speaker stuff. I'm sorry to say, yeah, I don't. Has it?
Yeah, it seems a little
subsided,
bit
perhaps. Okay. Cool. Thank you. So, right. So anyhow, we have a way to sort of try to get a handle on where the culprit circuits are. And we don't see any particular structure here. We see that certainly longer sequences have a bit more model violation than others. Oftentimes, if you're looking at a 2-qubit GST set, you'll oftentimes see that the 2-qubit gate has a lot more non-Markovian error on it, a lot more model violation than the single qubit gates. You'll often see that it increases with circuit depth, but not always. It depends on a variety of things. But this is sort of part of the entrail reading that one engages in to sort of understand with one's quantum information processor. So if we go back to the Jupyter notebook, the last thing that we don't see is the MRB decay curve, because we have the same issue that we had with the previous notebook. But I am asking for a leap of faith in believing me that there is a very nice RB decay curve that we can generate, even though there is non-trivial extant non-Markovian noise. We can still get a nice decay curve. We can still extract an effective RB decay rate for these circuits. So I think that basically wraps it up for the code demo. I'll turn it back over to Erik.
Thanks, Kenny. Okay, so I just wanted to end this with mentioning a few of the open research problems, and by doing this, kind of reiterate that this whole code is written by our research group. Its primary reason for being and reason that we add to it is to do our own research and serve the community at large. And so we're really focused on cutting edge things that are upcoming and things that we still need help in implementing some of these things too. So that's a great part of it being an open source project. So some of these things happen to be extending of some of the routines to larger numbers of qubits, right? This is a pretty common desiderata for a lot of these characterization methods. Also looking at larger than gate level components in a model. Currently, these models that I've talked about model individual gates, but maybe we could model a sub-circuit as an individual piece, and thereby be able to model a larger overall processor than a model that just includes individual gates as their components. Including and being able to develop benchmarking circuits for larger quantum processors is another area. And then real-time methods for tuning up, where we have a feedback loop now between a processor and some kind of characterization protocol. The ones that we've talked about today use circuits, that experiment design, and all of those get run at once, and then there's post-processing done on that. Another mode of operation could be to take little bits of data and make little adjustments as you go, and that's an interesting thing that we're looking into. So with that, I'll just flash up a number of the publications showing that this software has been used in previous research, and draw your attention in particular to the one at the top here, which is a publication particularly about pyGSTi. And this is a great reference for folks who want to know a little bit more detail than this talk has been able to give. It goes through a lot of the same sorts of things and has examples with it. I'd recommend it if you're interested in more details there. And with that, I'd just like to thank you for your attention. Here's a number of perhaps useful URLs. Like Kenny said before, you are more than welcome to contact us with, to complain about bugs in the code, or to get advice about what protocols do I use. Here's a list of all the developers. Just Kenny and I gave the talk, but a lot of people have contributed to this. And you can email us at pygsти@sandia.gov. And I finally want to thank the funding agencies that made this work possible there at the right. So thank you again. And I think we can do questions if there's any time. I don't know.
And certainly thank you to Sarah and the Unitary Fund for hosting us.
Absolutely.
Oh, I should probably turn myself back on here. Thank you so much for this talk. I think I know that we've had a lot of kind of discussions both internally at the Unitary Fund on our research projects and folks in the community trying to figure out, there is kind of I feel like there's kind of a jump between, folks just kind of doing learning about quantum computing, running their circuits, and then like wanting to do big stuff and not really understanding like characterization is the bridge between those two. And as mentioned at the beginning, GST is a lot of work to implement. I would never suggest, I don't think I'd ever suggest anyone try and implement this themselves for fun. pyGSTi is a great package to use, and I've been messing around with it for my own uses. And I'm super glad that you guys could join us, and I think the losing my voice. The level of detail, like kind of showing the components, really helps at least me understand what's going on under the hood, so that like I know Python, I know I can, with the reports and looking at the kind of the table of contents that you have on the results objects, that's cute. So it looks like we have a question real quick from Nathan, who says, do you know of any folks or have examples of using GST with pyGSTi for PEC? So that's probabilistic error cancellation, which is an error mitigation method.
I am not familiar with anybody doing it. That's not to say that people haven't done it. I think that sounds like a really cool idea. I think my intuition is that would probably be a relatively straightforward thing to do, but I say that sort of coming from a place of deep ignorance with respect to PEC. So I suspect what would happen is, you try to do it and you discover there are some really interesting reasons why it doesn't work in an immediate straightforward fashion, but there's still, ways to get it to work, but then you sort of, learn a bunch of interesting science along the way. That's my intuition,
Yeah, it's kind of go ahead.
Oh, I'm also not sure. I don't have a deep background in PEC by any means, but one of the things that groups have done that I'd say routinely, groups will implement, usually it's the idle gate, and you can either implement that as a just waiting some amount of time, or you do some sort of echoing pulses. And you can compare using some of the tools in pyGSTi what the noise looks like on the gate with and without that. And oftentimes that tells a very nice and consistent story. That when you apply some certain types of pulses, it will echo away the types of noise you expect it to, or it won't change other types of noise. So if PEC at all kind of fits into that picture, I think that would be a really neat thing to do. And I think it would be useful in that regime too.
Yeah, absolutely.
Yep.
Oops, I was muted. Okay. All I was saying is the context on that is that at the Unitary Fund we work on a package called MITIC, which is an error mitigation library, and which has PEC, ZNE, and a few others implemented. But it's kind of a funny one. You need to characterize the noisy systems to be able to mitigate them, but also to characterize, you probably don't want to mitigate all the errors. So, like, you want there to be errors when you're characterizing, but then you want to immediately get rid of them when you're running stuff. So, yeah, it's definitely that's kind of one of the places that kind of our interest in using GST has come from, is like, how do we, for these variety of different error mitigation methods, which, kind of sit somewhere between just running your circuit and full fault tolerance, because that's way out of scope for NISC devices. How can we make actually running our circuits on NISC devices better? And so, yeah, that's at least something we've been playing around with and trying to figure out how we'd basically be in probably that second mode use case where we have some of our own Python code running, and we'd, kind of interlace or call different parts of pyGSTi as we went. But
yeah.
Maybe another quick question. I'll try to wrap it up here real quick. But one, like, if someone was interested in contributing to pyGSTi, is there something in particular, like, do you have tagged good first issues? Is there like a feature that you're like, oh, I wish somebody could help us out with this? We don't have any, we're not resourced to do this right now. What would be like your top request?
Yeah, well, I think that that's a great question, and I do wish and I hope that we're able to evolve more into a lot of there's machinery on GitHub that can make this pretty slick, but we don't use any of that currently. I think you would need to contact us and we could have a discussion about it. I think things that come to mind are there are several like small things in some of the optimizations that could be updated. Some of the convex optimizations that we do, we know of ways in which they're not quite as efficient as they could be. There are, if you're into more of the like the visuals and like web programming, all of the stuff surrounding those reports that you saw, that's an area where there's a lot of work that we've kind of been putting off because it's just the GUI or whatever. And so there's a lot of things that surround that. Yeah, there's a list. I have lists on my computer and I probably won't remember them all now, but there's certainly a lot of things that that we need done. And so, yeah, I
Make them
realize
issues
that's not
then.
completely. Yeah, they're also fixing issues, right? If there are issues on and we do have some on GitHub, if there are those that you'd feel comfortable addressing, that would be awesome. I feel like for someone starting out, it depends on the issue, but it might be harder to get into it just saying like, here, go find this bug and fix it. I feel a little bad putting that on someone, but if they want to, I'd love it.
Yeah, no, what we've found, kind of in the Unitary Fund sort of community more generally, like a great way to onboard to a project is like go through the docs and find typos. Like it seems really small, but
Yeah.
it obviously improves the documentation, or like make suggestions for like, hey, I was kind of lost here. Can somebody
Yep.
help add more details? That's always a good way because then it means you're reading the docs, you're helping out the maintainers, and then that kind of puts you in a good place to then pick up like, oh yeah, there was this bug in this, in the report section or whatever, and then you can kind of dive in there. So I think, yeah, having just ideas and the issues from your lists on paper are always a good option to get the community involved for sure.
Yeah, and just another thing, just hearing you talk about that, Sarah, adding examples. One of the things that we would love to see grow from this is a resource where I don't know if you use matplotlib the way I do, but it's basically decide what I want to do, Google Stack Overflow, and then copy and paste some magic lines into a notebook somewhere. I'd love for there to be more examples of how users have found pyGSTi helpful. And so if you do end up using pyGSTi and you think like, well, I started from this tutorial that you had or this example and kind of made it better and did something new with it that you wouldn't mind sharing, that's another key way that I think people could contribute and make the whole software better.
Yeah, we are basically doing the same with Mythic too, trying to
Yeah.
Either solicit or encourage contributions of examples because it's a great feedback mechanism. I'll take one last question here. Something Aaron says, something that comes to mind is the tune-up/feedback structure between pyGSTi and other frameworks. Is there a need for a composer to effectively use pyGSTi in tandem with other packages?
Yeah, so probably composer. I could see there's different things that could mean. First of all, we need to get an idea of what the protocols we want to run. What are we trying to accomplish with this sort of feedback? Whatever it is, though, it will probably involve some sort of, we run some circuits, get the data for those circuits and make some adjustments based on them. That might be a fairly general framework for that. Certainly, there will need to be maybe a composer. I might have called it like a driver, something that knows how to communicate with hardware that also knows how to communicate with pyGSTi in that. And I think that sort of driver or composer component, if I'm understanding it right, there would need to be different ones of those, similar to how there are different device drivers on your computer to interface with different hardware. And that would certainly be a great way to contribute, and a way that I think we would need contributions, because we don't have the staff or really the funding to go and kind of make it interface with everybody else's hardware or something like that. So I think that would be a great way, if I understand it right. I don't know if you're getting any feedback from the question, but
and I
go ahead.
Oh, so, I'm sorry. All I was just going to add to that, I think, interoperability is something that we're very interested in, but we don't have a whole lot beyond these conversion methods for the PyGSTi circuits, and then we also have a bit of additional infrastructure for IBM jobs, but beyond that, right, we don't really have anything for really interfacing with other actual languages. And so, yeah, I mean, absolutely. We very much want our code to be as accessible and as useful as possible. And so to the extent that, some sort of compose or something like that would be helpful, that would be awesome.
Yeah.
So one quick related question, because this is something I'm also very interested in. We have similar problems with Mythic in that we support bunches of different front ends, bunch of different back ends, and we have to do all the conversions manually. How do you see like intermediate representations, whether it be like, I mean, OpenChasm 3 is kind of in that direction, but there's like LLVM based IRs, like QIR. I think there's also the one maybe you've been working on, Kenny, the Jackal, like it's also kind of an IR. Like how do you see like lower level intermediate representations working with PyGSTi, or kind of making it so that you don't have to have these like high level orchestration engines? You can just be like, here's the program, user, you take care of running it however you want.
That's a great question. I'm going to completely defer to Erik because it's also a hard question and I don't know.
Yeah. I'm not saying there's an easy answer. It's just I wanted to know your thoughts.
I think that's right. I think that is currently like still a research problem in my mind as to how to best do that. A lot of these QCVV methods desire control, a very kind of transparent control over the hardware, and being able to work with some of these like intermediate representations could seem really useful. And even currently, I don't know, it was probably went by so quickly, but when we interface with the IBM hardware, we kind of insert lots of barriers and things to try to keep anything else from happening that that would normally happen under the hood on a normal chasm file that you would write. So you get kind of this sort of awkward chasm that it can produce to try to keep that to a minimum. But yeah, I don't have much more to say than that.
No, that's totally fair. It's something I helped run a workshop at IEEE where we were discussing this, like how do you make it easier, because as maintainers I feel like it's something we shouldn't have to every one of us maintain all the conversions between different things, like how much like my brain goes crazy as to how much dev time gets spent on doing the conversions and stuff. And I mean, I don't know the right answer, but it seems like we should think about that. and lots of people are, and trying to find solutions there. So
we should just make a new standard.
Okay, I'm gonna like put the XKCD that's like, we need a new standard. All right, now we have a 13th standard.
Yes.
Yeah, that's...
Yeah,
anyway.
Right. It's right. It's funny because there are ways in which it's true and in ways in which it's, it seems preposterous.
Yeah. So I want to wrap up here to be, this has been a really great one. I wish we could talk for like another like 2 hours because I have so many more questions, but we can, folks can get a hold of you by emailing pygsty@sandia.gov.
Yep. Yeah.
And I will close with one question, which is, what is your current favorite board game?
Let me...
It's quick, like, what's your first gut reaction?
I feel like it's a cop-out to say pandemic these days. I think maybe Splendor. I think, which by the way, I think I can blame you for introducing me to, Sarah. So thank you.
Oops.
I'm going to say Carcassonne.
Nice.
Excellent. How about you, Sarah?
That's a good one. Oh, that's a good question. Shipwreck Arcana.
Oh, I don't know that one.
It's
You guys
a fun.
know much more exotic games than I do, I think.
It's a fun collaborative one with kind of a tarot-based theme. So, check it out.